Hello, everyone.
Let me know if you need to close the door.
Okay, we're going to be talking about zero-knowledge proofs in here. If you're in the wrong room, now's your last chance. Otherwise, this is going to be mostly kind of pencil paper, pen paper kind of thing. No need for laptops. I'm not going to like police people and tell them to put their laptops away, but we won't be using them. All right. So last minute, I found out that I get a whiteboard, so I've modified things to use that. And I guess the first thing, which used to be on a slide, is just kind of a game plan. Oh, thanks. Oh, I have an eraser as well.
That's okay.
Thanks. Cool, so I'm going to start with some demos just to kind of get our creative juices flowing. And then we're going to kind of give an initial definition for what zero-knowledge proofs are. Then we're going to come up with a couple on our own in groups, and well, quite a few anyway. And then we're going to talk about some bigger results, and then if we have time, we'll talk about Schnorr and some other stuff.
And I do just have one more administrative thing.
Go for it.
There are going to be cameras here, so if you don't want to be on camera, it does look like there are a couple spots in the back over there that you can shift to, just so that everybody is aware. Thank you.
Alrighty.
What's this talk about? I forgot.
Zero-knowledge proofs.
Got it.
Yeah. No, so, okay. I'll start with some demos, and then we'll talk about what zero-knowledge proofs are. So, I guess hopefully people can see that I've got 2 coins here. Let me just take a look at them. Yep. Okay, so I am going to prove to all of you that these 2 identical looking coins are actually different and that I can distinguish between them. So can I have a volunteer as a verifier? Okay, awesome. So I'm giving you this on the right and this on the left, and I want you to put them behind your back and either swap them or don't. I won't look.
What if I dropped one?
You have to keep track, so we can just do it again.
I'm kidding,
Okay.
I've got them.
All right, so you know whether you've swapped them or not?
I do.
Okay, can I take a look at them?
No.
Please?
Blind signature.
You did not swap them.
You're correct.
Okay, well, you know, I could have just gotten lucky, so let's do it again.
Okay, it really did go.
Did you keep track even then?
Yes.
Awesome, let me look. Okay. You did not swap them.
Good job.
Okay, let's do it one more time just for good measure.
All right. I'm going to switch it up this time.
Okay. I wonder what will happen. You did.
I did.
Awesome. Okay. So, hopefully, I've not told you anything about how I've been distinguishing them. But how convinced are we that I actually can tell the difference between these 2 coins, assuming that he's not a plant?
Yes.
Okay. How convinced are you, I guess, is maybe the better question. Since
3
you know you're not a plant.
3 out of 3%.
3 out of 3%. Hopefully something more like 7 out of 8.
No, I've only got 3 data points to go on. I would like 16 to be 98% sure.
Well, if I had more time, perhaps we would. But I'll move on to another demo. But I guess I'll just mention. So, if I didn't distinguish between these 2 coins, what would be the chances that I failed if we did it once? That's kind of a simple question.
50%.
Yeah, 50%. So we've got like a 1 in 2 chance that I fail if I can't actually distinguish between the 2. What about doing it twice in a row?
4 out of 2%.
I heard a lot of things. I hope someone said I have like a 1 in 4 chance of succeeding. Sorry? Oh, someone said it. Awesome. Okay, cool. And then, we did it 3 times, so what was my chance of succeeding if I couldn't actually distinguish between them?
1A.
1A. It gets cut in half each time, because there's a 50% chance I fail each time. So that means that you should be 7/8 sure that I can actually distinguish between these two things. And as you mentioned, if we do this a bunch more times, then eventually, you should be pretty sure that I can actually distinguish between these.
Is that an N?
That is an N, I'm sorry. Yeah, my handwriting will be a problem throughout this talk, so bear with me. All right.
Quickliest N I've ever seen.
For my next demo, I'm gonna pick a card. Actually, I'll have someone else pick a card. Pick a card. Okay, first of all, everyone believe me that this is a normal 52 card deck. We don't have time for everyone to go look at it, so I can take my word. But okay, do you wanna
Sure.
pick a card?
Yeah.
Go for it. Okay, cool. And now I will prove to everyone else, without telling you anything about his card, that his card is red. Here are all of the black cards in the deck. So, if you want to take a peek, make sure that I got all of them. They should be in order, so that should help. All right. Who's convinced his card's red?
Yeah.
Woo. Okay. And hopefully you don't know anything about his red card, other than you. That's not important. It was red. Woo. Okay. Last demo before we do some fun stuff. So who here doesn't know what Sudoku is or how it works? Awesome. Cool. Good crowd. Okay. So, and this will be the quality of our eraser, which is fine.
Should have used mine.
I can still use yours. Okay, I'll use both. Okay, so I don't have time to actually show you a full 9x9 puzzle because this would take far too long to reset up each time. But we're just going to do it on a 4x4, and you'll get the idea, and then you'll see how it works for 9x9. And it works for any size, really. You can go higher. But okay, I'm going to have a nice 4x4 Sudoku where I use the numbers 1 through 4, and there are 4 rows, 4 columns, and 4 2x2 grids, which I haven't really delineated very well here, but there they are. And then it's the same normal rules as normal Sudoku. I need to have 1, 2, 3, 4 in each row, in each column, and in each 2x2 grid instead of 3x3. All right, so here's a puzzle. And this isn't actually too hard to just figure out on your own, but you'll get the point anyway. So I'm going to prove to you that I know a solution to this mini Sudoku puzzle without telling you anything about it. That's my goal. So here in front of me, I hope people can see, otherwise I'll just describe it out loud. I have laid out a bunch of index cards with numbers on them, and I flipped over the initial kind of conditions, 3, 3, 1, and then I'm going to want a new volunteer from the audience so that eventually we'll have used everyone and you'll know that no one's a plant. Well, most of you anyway. Who wants to volunteer? You'll just have to shout random numbers at me. It's not that bad. Ah, awesome. Okay. So I'm going to give you 3 things that you can check about my solution that I claim I have here. You can check the rows, the columns, or the 2x2 grids.
Okay.
Pick one.
I'll check the 2x2 grid.
2x2 grid, okay. So people sitting up front, and hopefully other people can see, I'm clumping them into 2x2 grids. And then I'm going to shuffle each of these as I walk towards you, and check that those are the numbers 1 through 4.
They are?
Okay. Also, if I messed up, it kind of defeats the purpose of some of the demo, but hopefully you can all believe me.
Okay.
Awesome. I guess he doesn't technically have to check this one, but...
Yep.
Well, you could have more.
Oh yeah, that's right. I could have had more ones than other things.
Yep.
Awesome. Okay, so we had a verification that those 2x2 clumps were indeed the numbers 1 through 4. Now, just to convince you further, So first of all, think amongst yourselves while I set it up again. How convinced should you be so far that I actually have a solution to this puzzle? And you can talk amongst yourselves. Don't be shy. Also, introduce yourselves to each other if you haven't already.
Need more
I think
information?
1 out of 3 because there's 3 rules of verify and we verify confidence. Or he verified confidence.
For the revealed initial state numbers, you would have to know those initial states, right? Which ones were the initial states?
I don't think so.
Because we have to know which ones were revealed originally.
I don't think he does. Especially if he didn't go to nothing was revealed.
Approximations to share. Shout it out.
1/4, 1/16.
1/4, 1/16. Any other guesses? 1/3. Okay. So, I mean, okay, technically, you have a little bit of knowledge already because you see these things, but ignoring that, vaguely speaking, there are 3 things that you could have checked, and supposing that I didn't actually have a solution here, and that I just got as close as I could, the best I could have done is satisfied 2 of the 3 rules, right? Well, okay, wait. Maybe it's not possible to only break 1 rule? Okay, maybe I'm not going to think about it, but supposing that it's possible for me to just break 1 of the rules, then it's kind of like playing rock, paper, scissors. Yeah? Without ties, I guess. But yeah, so it's going to be about a 1/3 chance that you catch me in my lie, because I had to break 1 of the rules. So it's actually, I should say, at least a 1/3 chance. It might be higher than that. But I don't want to think too hard about the probabilities, because we're just going to repeat it over and over, and the same kind of thing will happen as last time. If I had a 1 in 3 chance of getting caught the first time, if we do it again, then how likely am I to be caught? How likely am I to succeed if I didn't know the answer, is what I meant to say. So actually this should be 2/3 to start, right? There's a 2 in 3 chance that I don't get caught if I'm lying. And then that becomes 4/9. So you'll notice this number is getting smaller. This is bigger than a half, that's less than a half. So my chance will still go to 0 eventually, maybe a bit slower. But okay, what's another thing you want to check?
I want to check columns.
Awesome. And you're allowed to check the same thing, but also that wouldn't be very fun for a demo, would it?
But Nadav, what if you set it up differently this time?
Good question. As I shuffle these up, think about this. Good question. And then tell me when you have an answer.
I have.
Go for it.
No,
Why not?
because I talk a lot, and I don't want to keep doing that.
Yeah.
I have a question. Right now, like as the game stands, you've made 2 guesses about what's in the board. That's the 1 and the 3. Is that right?
No. So these are the given kind of in a Sudoku puzzle.
so
It comes with given numbers, and then I claim I have a solution to what goes in the rest of these squares.
And now he's trying to prove it without
Telling you
showing
anything
us the
about it.
solution.
I know someone could have learned that there was a 3 in this column.
I want to specify, should I be keeping track of what columns you're giving me?
No, just checking that all the columns have the numbers 1
Just
through 4.
that they
in them.
have the numbers 1 through 4.
Yeah.
What about the order? Is the order?
No, because I shuffled them up
Shuffled them up.
before I gave them to you.
I see.
So to answer your question, so it is possible that I am changing it up, but really, I guess then what you should believe that I'm proving to you is that I know at least 1 solution. Because if I don't know at least 1 solution, there's still going to be this 1/3 chance that I get caught each time. And so you should eventually still catch me in a lie, even if I'm changing it up. Which is kind of why I alluded to it kind of being like rock, paper, scissors, in the sense that I'm also making a move here, but if you're just choosing a random thing to check each time, then that's the solution.
As a proof that you're putting the same board down every time.
Yeah, so I am not necessarily...
Hash it,
Yeah, I'm not necessarily putting it down the same way each time. And we checked them?
Yep.
Cool, so we should be more than half sure that I actually do know a solution to this very easy puzzle. Awesome, and we could repeat. And, if you think about it, this is like about 1/2, so if we do it twice, it's kind of like the last case. It just takes twice as long. Not too bad. Okay, so we have some examples of zero-knowledge proofs. Yeah, questions?
Do all zero-knowledge proof protocols involve this property where it's asymptotic to 0% chance, but it never actually reaches 0% chance that you're cheating?
Most, yes, but my card trick was not. It was right away, you should know.
That it was red.
It was red, exactly. So yeah, that still counts, I guess, as a zero-knowledge proof. But yes, basically every actual zero-knowledge proof, like I don't know how to come up with an analogy for how this would work on a computer, like with the cards.
It feels like it feels kind of like if I have a coin and I flip it, and then they're like, I'm not going to tell you what I got, but I will show you that it's not tails. Like that seems like it's a full knowledge proof, not a zero knowledge proof.
Say it one more time.
If I flip a coin and then I show you the side that it didn't land on, and I say that's a zero knowledge proof because I didn't show you the side it did land on. Feels like it's still that's what you basically did because there's a card with either red or black and you showed it's not black.
Yeah, so I guess, right, in that side, I would be proving that it's not tails or something like that.
Right.
Which isn't a very interesting proof to do in zero knowledge because the statement that I'm proving, it kind of gives you all the information.
Yeah.
And in most zero knowledge proofs, you're proving a statement like my card is red, where there's more information that I'm not showing. And so that's kind of the distinction. Flipping a coin and showing you the side that it didn't land on would still be a zero knowledge proof technically, but it's kind of like the degenerate case of like n equals 0 or that kind of thing.
So it'd be more meaningful if you had like green cards and blue cards.
Yeah, or like a 10-sided coin and you showed me that it was like not 4 or something. Yeah. Okay. And so for example, we could have used this card trick to show you that my poker hand is a flush or something like this without telling you what it was. If you're only willing to pay me like 2 coins to see what my hand was or something like that for those who play poker.
Wouldn't a more classical example be that you prove that you know what the card is without revealing what the card is or anything else about
Yes,
the card?
but that demo is much harder. Yes, but feel free to come up with that after the workshop and I'd be happy to hear it. Okay, so I'm gonna do one really quick thing and I'm gonna kind of change this Sudoku demo slightly so that you can kind of see how this would actually work in like kind of a computerized setting. Because I kind of took advantage of the fact that I can physically shuffle the cards, and I took advantage of the fact that you could see that I like followed the rules in terms of the columns and the rows and the 2x2 grids with respect to kind of these initial parameters. So what I'm going to do is I've written down some like permutations here of the numbers 1 through 4. I haven't written all of them, I really should have, but that's like 24, and I wasn't going to do that, let alone prep all of those. So I'm just going to pick a random one to begin. Okay, and then I'm going to set up one more time. Oh boy. Let me figure out where on my cheat sheet I'm supposed to be looking. Ah, convenient, okay. So I'm going to set up one more time, but this time I'm not going to flip anything over. So what's happening here on my computer is I'm sending you a bunch of encrypted values, one for each square on the grid, which you are receiving, and to you they look like nonsense. It's just a bunch of random garbage because it's encrypted. And I also send you encrypted what permutation I used of the numbers. And now, this time, you get to check one of 4 things. Is that right? No. You get to check one of the rows, one of the columns, one of the 2x2 grids, or my initial setup. So in total, there are 4 rows, 4 columns, 4 2x2 grids, and 1 initial setup. So there's 13 things, and you get to check one of them. So, my volunteer, which would you like to check?
In a computerized setting, I would probably want to check one of the 2x2 grids.
Okay, which one?
That one.
This one?
That one.
Okay. So, alright, I'm just going to flip these over. So what I'm going to do is, I was told this 2x2 grid, I'm going to just send the keys that decrypt these values. So it's just going to flip them over. And as you see, they're the numbers 1 through 4 in some order. Okay. What have you learned?
I don't even know what the question was.
So I claim to have sent you, encrypted, a solution permuted. So I took my actual solution, and then I just changed every 1 to a something, every 2 to a something, every 3 to a something, and every 4 to a something. So I've shuffled up my numbers, so to speak. So these numbers don't actually represent the numbers in my actual solution. In some sense, they're random. And you get to see 4 of them, and you just check that they're all different. So you got to check either a 2x2 grid, a single column, a single row, or my initial setup. Now, I don't want to set this whole thing up again, so let's say that you didn't see that. It's important that you didn't see that. And I was asked to check my initial setup. That's kind of the new thing I'm introducing here, so I want to make sure that it's kind of clear what I mean. So what I would do is I would flip over the spots that are kind of initial, and you'll see that it's 1, 1, and 2, and I'd tell you what permutation I used. And you'll see that my 1s became 2s, which is why this is a 2, and my 2s became 3s, and my 3s became 1s, which is why these two things that should be a 3 are a 1. So that's how you would check my initial setup. But the important thing is that you didn't see this earlier, and we had already re-scrambled everything, picked a new permutation, put it all down, set it up again, and I'm picking a new permutation each time. So really, once you see this, that was just making sure that I set it up correctly, and it's kind of, we said I have these 13 things. If I don't have a solution, I can't satisfy all 13 things at once. I must violate either the initial conditions, or one of the rows, one of the columns, or one of the 2x2 grids. So in this game, I actually have a much higher chance of getting away with it. I can satisfy 12 of the 13 rules, and I'll get away 12 of the 13 times that we do this. Right? So you shouldn't be very convinced that I have a solution after doing just this. But if we repeat it over and over and over again, right? 144 over 169, that's smaller. I'm not going to keep doing this, but it does get smaller. If you take any number less than 1, and you take powers of it over and over again, eventually it'll approach 0. And it'll do it quite quickly, exponentially. Less quickly than if it was like 1/2, sure, but right, if you just take until this gets to 1/2, that's like kind of your multiplier for how much longer it takes.
Is there a rule for when you can reasonably say you're fully convinced, even though it never goes to fully to 0, it's asymptotic, but what is like a best practice? Yeah,
so that depends on your personal morals, of how much risk you like in your life, what your epsilon is. So I guess in our setting, we're going to kind of just be caring that you can make it as small as you want it to be. And then in practice, there are a bunch of considerations that I'm not qualified to speak about for like what you should actually pick. So I don't know a great answer for that, but some super small number. Kind of the philosophy of people who like these kinds of proofs is that even if you're checking like actual deterministic proofs that aren't like not a conversation, just like a computer reading a proof line by line, there is some non-zero probability that a cosmic ray hits your computer in just the right spot and makes it a 1 instead of a 0 at the end when you're verifying whether your computer decided that it was a good proof or a bad proof. So you don't live in a world of complete certainty, so we can get down to those levels pretty quick, and then we should be happy.
So was this a non-interactive?
So this was definitely interactive. Yes, I was asking for...
But there is a way to do it.
There is a way to get it to be non-interactive, which hopefully we will have time for talking about. Definitely. Yes. In some sense, my verifier, all they did was they gave me a bunch of random numbers. And so I should be able to like replace them with a hash function or something. We'll talk about that later. But okay, let's define what a zero-knowledge proof is, at least partially now, that we kind of have a taste for them, unless there are any more questions about what we've done so far. Awesome. Okay. So, the one downside of using a whiteboard. In the future, someone should invent one that erases itself.
We should get some alcohol in here. For us, not for the board.
All right, so zero-knowledge proof, or ZKP. Since I'm writing, I'm going to be using acronyms. If anyone forgets what an acronym is, just shout at me. Or people next to you.
What's an acronym?
That I can't help you with. All right, so a zero-knowledge proof, this might not be very satisfying, is an interactive proof that is zero knowledge. So I have more things to define. I haven't actually given you very much. Okay, so an interactive proof is a conversation between a prover and a verifier that I'll call P and V, satisfying, and it's got two properties, completeness, so it should be complete, and it should be sound. Okay, completeness, loosely speaking, means that an honest prover always succeeds. Right? If I'm telling you that I have a solution to the Sudoku puzzle, and the proof we're going to use is I guess the next block hash, that's not going to be a complete interactive proof because an honest prover doesn't really have any way of succeeding. So we need that the honest prover not only mostly succeeds, but always succeeds. If I mess up, you should not believe that I know a solution, even if I mess up just once. Soundness, oh, I was inconsistent. Soundness means that a dishonest prover, which is to say a prover that's claiming to have a solution to some problem that they don't have a solution to, or for which a solution doesn't exist. A dishonest prover fails almost all the time. So here we allow some little epsilon, little Greek letter for meaning little numbers. And you should fail 100 minus epsilon. That is a terrible epsilon. 100 minus epsilon % of the time, where epsilon is small. Now the thing is, as long as I make sure that epsilon is positive, I can really set it to be whatever, because then I could just take this definition and a different definition with a smaller epsilon and just say you run this protocol 5 times, and then it becomes something that satisfies this. So it doesn't really matter for our definition what we set epsilon to, because we know we can always kind of repeat and get that probability down. So long as if I wanted to throw a mantra at this, it would be if you can fail, you can't avail, for dishonest provers. Yeah?
With the red-black card example, is epsilon 0 there because there's no...
Exactly. So that's kind of, for your previous question, it is possible to actually get to that 100. Normally it isn't, and this isn't really a great example of how things work in the real world. Usually there is some kind of epsilon involved. All right, what's zero knowledge? I'm not going to fully answer this one, because we're going to kind of iterate on what we think zero knowledge should mean. But loosely speaking, I hope people can say, but I'll say it out loud as well. Zero knowledge means that the verifier learns nothing other than the statement being proved. So you have some zero knowledge proof of a statement if you have a conversation between a prover and a verifier where an honest prover always succeeds, a dishonest prover almost always fails, and the verifier learned nothing other than what the prover was proving. So in our example so far, hopefully you learned nothing about my 2 coins other than that they're different. You learned nothing about his card other than that it was red. And you learned nothing about my solution other than that I have one. It's kind of the idea behind zero knowledge here. Any questions about our definition so far? We'll make it better.
So what is knowledge? Is there there's a difference between knowledge and information or data or whatever?
Yes. What is knowledge? Okay, so I was gonna iterate about this later, but I'm gonna change it slightly. I'm gonna say V learns nothing useful other than the statement. So in some loose sense, they shouldn't be able to do anything after talking to me that they couldn't do before, other than repeat me. But we will get more into kind of what this means. I've left it kind of intentionally vague. And then after I make you come up with a couple zero-knowledge proofs, we'll kind of figure out what we think this should mean, kind of make it more precise.
If there's a person between P and V, an intermediary,
Mm-hmm.
and that intermediary is he's forwarding messages from P to V, it seems like it is possible for V to think that he's talking with the intermediary.
Yes.
And he's really talking with the prover.
Yep, it is definitely possible to do a man-in-the-middle attack in these kinds of things, and there are kind of some of the usual man-in-the-middle attack mitigations, and then there's making things non-interactive, which is kind of the favorite of people who do zero-knowledge proofs. But for now, we will pretend like there are only two people in the universe, and one of them knows everything and one of them knows nothing, something like this. And then we'll build a more real world from there. But good question.
What is a non-interactive?
Non-interactive just means that it's a conversation where only one person speaks.
Okay. A monologue.
Yes, exactly. Okay. So now is when I am going to kind of send you off to talk to the people around you and come up with a solution or a conversation that a prover can have with a verifier to convince them of something. Well, let me set the stage first. Sorry about all the noises. All right. So I want to kind of just remind you in our two-coin scenario, the conversation, here's kind of a way that people draw zero-knowledge proofs. Sometimes you've got a prover, a verifier, time goes down, and then what happened is I had coin 1 and coin 2, which I gave to the verifier, and then the verifier kind of decided for themselves whether to switch or not switch. And they should have picked randomly, 50-50, just as they were. And let's call we have this function f, which if they decided to switch, swaps 1 and 2. And if they decided not to switch, sends 1 to 1 and 2 to 2. So one way of writing this down is they respond with the coins C f of 1, C f of 2. Like this, and then the prover has to respond with what f is, whether they switched or not. And then the verifier checks, or I guess f prime, and then the verifier checks, does f prime equal f? So this is kind of what I did earlier, which I want to remind you of because it'll be useful in solving this next problem, which I just realized is about graphs, so I should probably review what graphs are just in case, but I'm sure plenty of people here are fans of the Lightning Network and have seen a network kind of graph before, but all it is it's a bunch of vertices. I had a couple specific examples I wanted to draw. So we've got a bunch of vertices or nodes, and then we have a bunch of edges or connections between them. And this is one of my favorite graphs, despite the fact that it looks a little demonic. It's called the Pedersen graph. And it's like the smallest counterexample to a bunch of things in graph theory. And I drew this here still. Let me make sure I get this right. And then over here, I've got another graph. Let's see if I can get this one. Oh, that's not right. Darn it. Sorry. Let's fix that. There we go. There's another graph, and I don't know, here's another. Let's just draw some stuff. This, is a bad Lightning Network right there. You don't want that. If you can see what I've drawn. Okay, so there's a notion under which these two are actually the same graph. I've just kind of moved all the nodes around in my picture, but they represent the same relationships between people. And a formal way of kind of saying this is that there's a function f. So we call a graph is just a set of vertices and a set of edges. Or a set of nodes and a set of connections, or however you want to think about it, but that's what a graph is defined to be. So I have one graph here, I have another graph here, and we say that these two graphs are the same if I have a function f from this set of nodes to this set of nodes. So I'm just saying like this is that one, or something like this. So from v1 to v2, which oftentimes we just write g1 to g2, because maps on graphs are always just about the nodes. Such that, so it satisfies the property that v is a neighbor of w if and only if f of v is a neighbor of f of w. So the map, if I have two nodes here and I say that they correspond to this node and this node, they're connected. If these two are connected, then these two will be. And if these two aren't, then these two aren't. So it's kind of a structure-preserving map. And we say that these two graphs are the same if there exists a function that just, essentially if you can tell me exactly which node corresponds to which node, and all the connections are the same. So we have an example with the two coins of a zero-knowledge proof that two things are not the same. So here's an example of two things that are the same. Here's an example of these two things are definitely not the same, right? Here we have a vertex of 1, 2, 3, 4, 5, 6 neighbors, and there are no 6 neighbor vertices here. So there's no way I'm going to be able to create such a map. So these two are definitely not the same. This just kind of captures what we mean when we say things are the same, because we don't care about how you draw things when it comes to graphs, almost always. Okay, so the zero-knowledge proof that I want you to talk about with your friends, using this as kind of inspiration, along with kind of what we've seen so far, is I want a proof. Is it okay if I erase this graph? Okay. I want a proof that two given graphs are not the same. Oh, there's one important thing I forgot to mention. For the prover in a zero-knowledge proof, in almost every actual use case, they have to do things quickly, right? In cryptography, we don't like slow things. But technically speaking, for the definition of a zero-knowledge proof, the verifier has to do things quickly. They have to do things in polynomial time efficiently. They can't brute force things that aren't quick to brute force. The prover, however, has like infinite time and infinite computing power, and the verifier remains dormant and frozen in a cryogenic chamber while the prover is doing their computations, or you can just say the prover does computations instantly or whatever. Later, we'll reintroduce normal things, but this is, I have to go through some weird, contrived examples in order to get people to be able to come up with things on their own.
Wait, so. The verifier has infinite time, but the prover?
The prover has infinite time. The verifier has is a normal compute, like a Raspberry Pi or something. It can't do very much. Okay, so
I think they can do a lot.
Graph non-isomorphism. I'm not going to spell that. Okay, so I have a graph G1 and a graph G2, and they aren't the same. That's kind of the statement that the prover is proving. So I have a prover, a verifier, and I want y'all to come up with a dialogue between them with the people around you in which the verifier will be convinced that these two are not isomorphic. All right. I'll give you like a good 15 minutes or something. This is going to be the meat of the workshop. So make sure you know the people around you and get to it. I'll come around, and do feel free to just shout at me with questions and thoughts and things like that.
Is it not just the inverse function? Does not exist a function, hey, I'm going to graph function tells you that it's the same as
the timing is on point.
I think he's trying to ask us to come up with that function.
Or the conversation.
In a conversation, yeah.
Or not to, so there is no function, because these aren't the same, but you want to convince someone that these two things are not the same. In kind of a similar fashion to how I convinced you that these 2 coins are not the same.
I can't just answer saying, why can't I do the prove that, try and prove that it is the same? And if you fail immediately, then...
because then a dishonest prover could just pretend to fail, even if they were the same.
That's a
good question.
Yeah, so I think the idea is like you can
So you gotta. So I think the verifier has to ask the prover question.
Iterate over every one of your shells on the other one. You can find that.
So maybe he could say.
He already knows whether or not.
What can he say? How much knowledge does the verifier have about the graph? Does he know how many nodes there are?
Yeah, so the graphs are known publicly to both parties. G1 and G2 are known.
He doesn't need the prover. He can prove it on his own.
It turns out that it's not easy to determine whether two large graphs are isomorphic or not in like serialized versions. So a serialized G1 and a serialized G2 are known.
The prover can prove it, then the verifier can do it.
No, because the prover has infinite time and the verifier can run polytime algorithms. At least 3 more of these kinds of think sessions together for other problems. I kind of want to bring us together and see what kinds of just ideas we have and see if we can piece them together into a solution. So I'm not asking for full-fledged solutions, but what are some like vague, if need be, thoughts that people had that might help us in doing such a thing? Just blurt them out.
Is there a good one we had over here was just like asking whether or not 2 nodes share an edge, or 2 points.
Asking whether or not 2 nodes on
both graphs. Like, so I would ask if I.
So this is the verifier asking?
Yeah. This
Okay.
is the verifier asking the prover whether or not 2 nodes are sharing the same edge.
So we're sharing the same edge. I see. Like you point to 2 edges, one edge here and one edge here, and you ask if they're the same? Got it. I'm a little worried that that's information the verifier doesn't already know.
I mean, the graphs are public information. The problem is that the mapping between the 2 graphs is unclear, especially since they're not.
Yes, so there is no notion of edges being the same because there is in fact no way of kind of corresponding them in this scenario. Yes, so we're doing graph non-isomorphism zero-knowledge proof here, kind of like how the 2 coins were not the same. But hold on to this idea. Later when we do a different proof, this kind of thing will actually be exactly what we need.
What's it called when you take a graph and then morph it so that it looks different but still has the same edges and stuff?
Permutation. So it's kind of a way to shuffle a graph. This is a good idea. It doesn't take any time. A verifier could take one of the graphs and they could shuffle it up and keep track of the shuffling. The shuffling is just like a permutation. So say that graph 2 has like n vertices. Sorry about my n's again. But if you just have like 1, 2, 3, ... and then kind of like I did in Sudoku, maps to what they go to.
I have a suggestion.
Okay.
You take both maps, graphs, you shuffle them.
Okay.
So they're both different looking now, and you put them in an array that has 2 items, which is both graphs.
A little tuple.
Yep. Then you swap them or keep them the same, like we did with the coins.
Okay.
And you ask the prover
whether or not
did I swap them.
Cool. So written, we could say the verifier generates 2 permutations. Since P is kind of like for provers, I'm going to use a Greek P or pi. Sorry to people who are used to seeing pi as a number. In cryptography, we use pi as a function all the time. So we've got pi 1 and pi 2. Say 2 shufflings. You could even use the same one. I don't think it would matter too much. But okay, this is just like mapping the numbers 1 through the number of nodes to 1 through the number of nodes. And then you send over either pi 1 of G1, pi 2 of G2, or you send over pi 2 of G2, pi 1 of G1. And then what does the prover do?
He tells you whether you swapped them or not.
Yep. Cool. What do we think?
Well, you wrote it down, so I'm confident.
You're using meta information here.
Fair enough. Okay, yes. There are other solutions to this, just to be clear. This isn't the only solution. What's up?
I would just send over one of them, like one permutation, and ask the prover to tell us which preeminent graph it corresponds to.
Very cool. So a little optimization, as we could just write down come up with one random permutation and one random bit that's either 1 or 2. And then we send over pi of GB, either pi of G1 or pi of G2. And then the prover tells us which one you sent over, and then we check, is B prime equal to B? Is it the correct? If you sent over a permutation or a shuffled version of G1, they should say 1. If they sent over a shuffled version of G2, they should say 2. Okay, let's run through the definition of a zero-knowledge proof and just check that it has the properties that we want. So, okay, first off, completeness. If these two are not the same, will an honest prover always be able to succeed here? I guess, yeah, so long as you know that, you can just brute force the answer. Like, right, you can look at all possible permutations, which is like far too big, but the prover has infinite time or whatever, and they can look at all the possible permutations of both graphs. They can just write down those tables and then search them for this. And if these indeed are not the same, then those two tables won't be the same. They'll be actually entirely different from one another. They'll have no intersection. And you'll be able to tell which one it was on. So it is complete.
He's using a Raspberry Pi 4, which makes it easier.
you might, the prover might want a Raspberry Pi like 4000 or something. I don't know. But okay, is it sound? If the prover is dishonest and these two graphs are actually isomorphic, what are the odds that they fail?
50%.
50%, right? Because they're going to either say B was 1 or it was 2. So they have a 50% chance. If these two are the same, then this gives them no information. It tells them nothing. It's a random shuffling of both of them. So all they can do is just shout a random number at you. And they only have, at best, a 50% chance of succeeding each time, which means that if you do it n times, then they'll only succeed 1 out of every 2 to the n. So that's good. That goes to 0.
So is it sound or not?
It is sound, because them succeeding goes to 0. So that's epsilon, a dishonest prover, that is. Yeah, you could also think of it as, they have a 2 to the n minus 1 over 2 to the n chance of getting caught, so to speak. So this should be convincing. Sometimes I say sound and complete. I call that convincing. I don't know. It's not standard. Okay, is it zero knowledge? What do people think? Did the verifier learn anything that they didn't know ahead of time? Anything useful?
Well, they only learn whether it is one graph or the other each time. And that doesn't reveal anything about the graph.
They know that already also. They shuffled it.
Yes. So it turns out nothing said was wrong, but we are kind of assuming that the verifier is honest in this argument. If the verifier, technically the protocol just says verifier gives you a graph, and then you respond with a 0 or a 1. If the verifier gives you a graph that they didn't actually make, that they found in the wild or something like this, then they could learn something about that graph, which would be bad. So we call this, and this is not a big problem, this is going to be fine, but we call it honest verifier zero knowledge, or HVZK. So in practice, honest verifier zero knowledge is almost always good enough, because we're going to get rid of the verifiers later and replace them with hash functions, because it's just spitting out random stuff. So we won't need verifiers forever. So honest verifier zero knowledge is oftentimes good enough. But I just wanted to make note that this is only zero knowledge, assuming that the verifier actually follows the rules.
What was the knowledge being hidden? Because the verifier knew both graphs.
Yes. So for example, say that the prover had like some tricky way of distinguishing between the two graphs, like I did with the coins. There's like a trick.
Yeah.
They have a difference in them, and so the verifier didn't learn anything about how these two graphs are different, for example.
Okay.
They only learned that they are different. They learned nothing other than this statement, assuming they followed the rules. Because we told them something they already knew. Right? They came up with B, and we just told them B right back to them. So one way of making sure that you're zero knowledge is to never tell the verifier anything they don't already know. And this isn't really practical in general, but it is a useful kind of like thing to use every once in a while, is that You certainly haven't told the verifier anything they don't already know if you just tell them things that they came up with. It's kind of like we did in the coin situation. I only told you whether you swapped it or not behind your back. You already knew that. Okay, so this has been cool. But so far, I mean, it's not really all that interesting to show that two things are different. I think it's a bit more interesting to show that two things are the same, that don't seem like they're necessarily the same. Like those two graphs that I drew earlier, they didn't really look the same, but they were the same. So imagine that, but like with giant, like lightning network-sized graphs. That's not going to be very easy to distinguish whether or not two graphs are the same. So next up, we're going to talk about the graph isomorphism zero-knowledge proof. So in this situation, I have two graphs, like written down somehow, but they're actually the same. So there is a function, f, that sends G2 to G1. Like it sends each node here to a node here, maintains all of the edges. And these graphs, again, are known, but this f is only known to the prover. The prover knows this f. You can think of it kind of like a private key. I'm claiming it's a hard problem. I'm claiming f is a private key. And like G1, G2 is a public key kind of thing, so to speak, hand wave. It'll be more precise later, hopefully. But I now want us to break up into groups again. We're no longer going to use the two-coin zero-knowledge proof for much inspiration, but keep in mind kind of what we've learned so far. If you have the verifier present challenges to the prover that they have any chance of failing, that's good enough, because if you can fail, you won't avail, right? We can just repeat over and over and over again, no matter how small that chance is. So that's one thing to keep in mind. And then probably, I mean, not entirely, but I would think more about our Sudoku example if you want inspiration. It'll be more like that than anything else we've looked at. It won't be exactly like Sudoku in the way that graph-anon isomorphism was almost exactly like the two-coin problem, but it'll have a similar kind of shape, let's say, and similar vibe, which we'll name. But okay, just to make sure everyone understands the problem, we've got two graphs that are known to everyone, G1 and G2, and only the prover knows this fancy f that is the isomorphism. It's a map, a correspondence between nodes of this graph and nodes of this graph. And the prover wants to prove to the verifier that these graphs are indeed the same without telling the map or anything about it. Yeah. It might be helpful with this one to come up with something that is an interactive proof that isn't necessarily zero knowledge at first, and then see if you can make it zero knowledge, but don't get too wild. Just like with the last one, nothing too fancy about like the actual internal graph properties should be necessary here.
Just before you say, can you just repeat like the constraints for the problem?
Yeah, totally. So we've got these two graphs, G1 and G2. Both parties know G1 and G2 and have access, they're written down somehow, list of nodes and their neighbors or something. And then the prover knows how to correspond G2 to G1. They're actually the same graph in the sense from earlier, right? Like if I have this graph and I have this graph, this isn't interesting, but these are the same, right? And I could say like 1, 2, 3, 4, 1, 2, 3, 4. This is actually like a correspondence between them. If you look at it, right, like 1 is connected to 2, 3, and 4. Well, 1 is connected to 2, 3, and 4, so on and so forth. They're all connected to each other. I could have labeled it any way I wanted. But these two are the same, and the prover knows how to say, like, this is that person. They have two ways, essentially, of writing down, or these are two ways of writing down a graph, and the prover knows which node in here is a node in here. And the verifier doesn't know this f. They only know the two graphs. And the prover wants to prove that these are actually the same thing, preferably in zero knowledge. Okay, let's do it.
So we can't shuffle down and ask for it. Just for the same. That's going to be trouble.
Sure,
Does say yes every time?
Well, is this where
this is
the example of, hey, I'm going to
I'm gonna send you a node and its neighbor.
I'm doing okay.
Well, that's the same thing. When you run the node and its neighbors through this function, do you still just want to add some of these neighbors? Sure.
Yeah, there's another black one back
Yeah, I
there.
was talking about small things that fail.
My timing is actually way closer to what I thought it was. Or I guess I intended it for it to be that way, but it never works that way. I've been like hitting every. I've got like little time stamps.
I guess you can like do both of the graphs.
Another like 7 minutes.
From the prover
We have to
side.
be here.
And then the verifier.
We might get to it.
Maybe ever. I wonder if we can take a subset of the graph and ask him about that subset. Subgraph. That's what we did with the Sudoku one. You said to use
That's right. That's right. And each time you're asking for a different subgraph, and you technically don't know if you don't actually learn.
I'm trying to think of
You want to pick a random subgraph, this subgraph have correspondence. Prove that it has correspondence.
Yeah, that's the thing. Prove that it has a correspondence. Oh, I have a question. Are we only allowed to ask him yes or no questions?
No, not necessarily.
So we can ask him to prove something to us?
Depends. Maybe.
Oh? Can you give an example of something we could ask him to prove?
Can we ask him to prove? I guess we would need to construct a proof that a random subgraph was actually included in the other graph, right? So we need a way to prove how would you prove that.
Yeah, that sounds like an equally hard problem to this one. You'd need zero knowledge proof. Yeah.
Show me this subgraph of the other graph. That's not zero.
So what's an example of something we can ask him to
Eventually
prove?
piece together and have
Let me think of one.
Thinking the same way last time.
This isn't part of the proof.
Yeah, I mean, normally you can get rid of the verifier, so they shouldn't be doing anything too clever, you know? I mean, okay, so sometimes, I mean, you can think of a random number as, like, a question. Like, it's a prove, like, 0 means prove this, 1 means prove this, 2 means prove this. Like, for example, with the Sudoku puzzle, you could have asked for me to prove 1 of 4 things that I followed 1 of 4 rules, that kind of thing. But really, it does almost always boil down to, like, say, a random number for the verifier.
But if you said
Can we compute the number of evidence?
For the prover or the verifier? So yeah, the verifier can do anything that's quick. So they have the graph, if they have a specific node in mind, they can look around. But they can't look around every, or no, they can even look around every vertex. So the size of the problem is the size of the graph.
But like,
so they can do linear things, quadratic things.
But stuff like pathfinding or shortest paths or whatever, it's not.
I mean, they could do approximations maybe, but this is not going to be helpful. Yeah, it's going to turn out to be of a similar flavor to what we've been doing so far with like a twist or two.
I think we have some rules that he has to follow.
And I've given a little hint on the board. Some arrows.
not have you go
make that sense.
Well, let's try to make Sudoku under that field. He showed us an initial
But that was shared.
Yeah, right? So would that be what we do?
Yeah. That's the setup, yeah.
Okay.
So here are the graphs you're doing. Before the graph was interactive. Yeah, before the
We're trying to prove that G1 and G2 are the same. Meaning G1 is just like some sort of where F is
makes
sense.
Yeah, verify.
Why are we able to get non-voice confirmation?
Some point.
So what are we trying to do?
How many, based on the amount of nodes?
Yeah.
Yeah, so the only issue is there are...
What are the rules here?
Technically, yes, it's the verifier doesn't have the memory. Or they can even process them. They can only do
It's true about that.
Yeah, and
they can come up with random shuffling.
That every
They can't actually
look at all clearly labeled. And one of it is
You know, it's actually not.
It's kind of like in Sudoku where I started with probably encryption here. They started with like some commitment information, you know, and then a challenge came to them.
So we need to ask
from the
questions.
verifier to prove it, and then they respond.
So what if we label the nodes on both graphs?
And then
we ask questions about
Both graphs on the same number of steps.
we pick numbers and asking questions about them. Like is node 1 or which okay I know what we can do. Which we pick a number on graph 1, like the number 2. We say on the other graph, which node is number 2?
All they can do is
And then when he gives us the answer, we check if it has the right number of neighbors. As ours. He's going to tell us number 5 is.
By doing that, reveal some of the numbers they have.
Okay, let's come back together and discuss what we have so far. I promise we'll be able to get back into our groups. We'll do another one after this that I think is more interesting. So I want to move this one along. Okay, does anyone have any ideas they like that they want to share with me? Brave souls.
Could you just permute the two graphs as the verifier and then ask if the two graphs are isomorphic?
The verifier. So you're saying the verifier permutes the two graphs.
So
I see. Okay.
It knows that they are isomorphic.
Mm-hmm.
So it basically builds its own F and then gets the prover to check it with their F, or is the F specific to those two graphs?
Or the F isn't specific to those two graphs, but I'm not sure I entirely follow. So they take these two graphs and they like randomly shuffle them up.
Yeah, they
and then what do they ask for after that?
If they are isomorphic.
And the prover responds with like a yes, no, or they respond with the isomorphism?
Well, I guess it's kind of the same as the last time. Well.
Yeah, I think you're onto something. They respond with the isomorphism.
I see. So the issue here, so we're saying the verifier sends over some pi1 g1,
writing it down.
pi2 g2, and the prover then responds with some like f prime.
He didn't say no. He asked for
That's an isomorphism between these two things. The issue is that the verifier knows pi1 and pi2, and so if they know f prime, they can compute f from composing the shuffling. So yeah, this is an interactive proof, certainly, but it's about as good as, just saying what f is, which is an interactive proof, by the way, showing just, this simple f. That's an interactive proof, but it's not zero knowledge. Yes?
Based on the idea that what if the verifier would either send a permutation of G1 or a random graph, and then the prover were to respond whether or not it is an isomorphism.
So you're saying G1, or you're saying like pi of G1, pi of G2, or
something completely random.
Pi of random.
G prime. I see. So I have a worry. What if G prime accidentally is the same as G1 and G2? Then it might not be complete.
Seems like you could do it 1,000 times.
Yeah. So there might be a way to do this, but it's always going to be a little tricky to construct a G prime. I mean, you could make sure that it isn't, but then you might learn something if you do it a specific way.
How about this?
Yeah.
The prover tells us a random node from the graph 1.
Okay.
We make up an isomorphism of graph 2.
Okay.
And we commit to Oh, never mind.
No worries.
Never mind, that doesn't work.
What's up?
Because we don't know the correspondence yet.
Another idea that we had was sending two vertices on G1 to the prover,
Okay.
and then having the prover send back corresponding vertices on G2, and then the verifier compares the number of edges and the pre-mentioned image, and keeps doing that iteratively.
But that way you just extract it.
Eventually, yeah.
Yeah. So this is a good example of something not being full knowledge in the way that just saying F is, but since this will have to be iterated over and over again, the reason that we require kind of zero knowledge to be so airtight is because you know, repetition just reveals more and more knowledge over time. But okay, I'll start us off. Though I've liked a lot of the ideas. So I'm going to start with the prover sending over, or generating some random shuffling of, right, they have the same number of nodes. And then sending over, I'll call it G prime. So they just send over a graph that happens to be, say, like pi of G1. So they send over a shuffled version of G1. And like always, I want my verifier to just kind of do something silly, you know, ask for one of two things. What could we do here? Well, the prover is claiming that this third graph is the same as these two, right? It's a permutation.
So is pi is the same as f?
No, sorry, G prime, which is the shuffling by pi. Pi is like a shuffling of the nodes. Just to
Creates another isomorphic
moving around.
graph.
Yeah, so this is just, these are all the same graph, is the claim.
Yeah. But pi is different than f.
Pi is a different shuffling than f is. Okay. Yes, exactly. Yeah. They're just, pi is just some random shuffling. Okay. And then the verifier can ask, give me an isomorphism from this random third graph to G1 or to G2, for example. So they're going to pick a B from, that's either going to be 1 or 2, not 1 or 3. And they're just going to say, like, give me an isomorphism to G sub B, to G sub 1 or to G sub 2, up to them. Flip a coin.
What's B?
B is just a random number between, or that is either 1 or 2 that the verifier decided. It's like they're swap or they're not swap kind of thing.
A 1 or a 2?
Yeah, they either send over a 1 or a 2. 1 is a challenge saying, give me an isomorphism from this to G1, in which case, right, so if B is 1, then they send over pi. Right?
Not inverse pi.
Pi inverse. Yes. And it's easy to flip a shuffling. You just reverse all the arrows. And otherwise, if it's 2, then we have to send them an isomorphism from G2 to this. So that's going to be, first you undo F, and then now you have G1, and then it's the same as last time. So you send them that shuffling.
Can we name that one Q?
So, sure, let's name this whole thing Q. And then the verifier checks whether Q of GB is G prime.
But wouldn't that be very expensive?
Which part?
Checking that these do match.
So applying shuffling, you're given the shuffling, it's like n size, it's the same size as the graph. And then applying it is, so...
Polynomial.
No, so what happens is we have to kind of think, in order to answer this question, of a specific way of writing graphs down. My personal favorite is called an adjacency matrix. So I have an n by n matrix. A row in a column represents a node. There's a 1 in ij if vertex I is connected to vertex j, and a 0 otherwise. In this case, these permutations are just permutation matrices. They're like shuffled up identity matrices. You have a 1 in each row and in each column, and 0s everywhere else. And then you just apply those on both sides. It's like a change of basis for people who like linear algebra, but if you don't know that, you can just take my word for it, I guess. But it's just going to be a matrix multiplication. And then you're going to have equal matrices after that. It's n squared, I guess. So it'll still be polynomial time. But yes, it is not obvious that this should be quick, but it turns out to not be too bad once you pick a serialization method.
Captain Crunch would be mine.
All right. So is this convincing? Sorry. Is it complete? Will the prover always succeed here?
Yes.
And not only will they just succeed, it's like quick. They don't have to do very much. They generate a random thing. They already have this. Inverses are instant to compute, and composition is matrix multiplication again. Yes. So like if I have this shuffle and then this shuffle, I can be like here to here to here. Just write down that. It doesn't take very much time.
And it's zero knowledge because if you do this a bunch of times, you'll figure out pi, not f. That's why it's...
Yeah, so I'm picking a random pi each time. So so this is a good question, though. Is this zero knowledge? And before I answer that, I've skipped one. Is it sound? If these are not the same, how often will the prover fail?
Almost all the time.
All the time.
So what if they say b equals 1,
Yeah,
for example?
Fail in the b equals 2 case, right?
Right. So it'll be 50% of the time again. They can, if these aren't the same, and the verifier is allowed to say, show me it's the same as this one, or show me it's the same as that one, they can only say, show me it's the same as one of them, not both of them. So it's only the same as one of them.
And also they can't prove both of them with the same random shuffling because then they actually tell you that.
Interesting. Keep that in the back of your head, I guess. All right, cool. So this is sound. And then to your question, is it zero knowledge? So what do we think? Did the verifier learn anything?
You learned Q. Q seems pretty useful.
Cool. So
only learns half of Q.
Half of Q. Same. What do you mean?
Well, depending on whether b is 1 or 0, you only learn pi inverted.
Pi inverted, f inverted. Gotcha. Yeah, I'm calling this Q though. The thing that the prover sends back is Q.
Oh,
so I think you meant half of like f or something.
Half of the two options of Q.
I see. Cool. Okay. So here is where we have to kind of be a bit more nuanced and answer our question from earlier about like what exactly we mean by zero knowledge. So I claim actually that the verifier doesn't learn anything useful here. I guess I'll say the hand-wavy version and then I'll say like how you actually make this precise. So the hand-wavy version is you either give them p inverse, which is the inverse of a random permutation. So that's just a random permutation. I just essentially tell them a bunch of random numbers. Or pi composed with my actual thing. Now you can think of this as kind of I have a number between this and this, and then I add a random number to it. You've actually, if I give you that sum, mod whatever, so you know if it like wraps around, if I give you that sum, you actually have learned nothing about my initial thing. So likewise, it turns out that that's actually going to be the same. If I have a matrix and a random matrix, and I multiply them together, I get a random matrix. So all you're giving them is a random matrix with random entries satisfying some rules in them. So that shouldn't really be useful. It's kind of like just saying a random number to someone. Did you really give them any useful information?
It's a cool number.
Cool. But, so that's a good point though. What if it's like a cool matrix or something? So here's how we make this a bit more precise. Another mantra that I came up with for this talk is knowledge is what you can do with it. So if you can't do anything new, you've gained no knowledge. So let's see. I claim that the verifier, without a prover existing, can like simulate the existence of a prover and come up with a conversation like this that is the same as this conversation without there actually being a prover. So what do I mean? A conversation here has 3 parts to it. It has a G prime, so a graph that the prover sent over. It has a B that the verifier sent over. And then it has a Q. And it satisfies the property that Q of G sub B is equal to G prime. Right? But other than this property, what do we know about these 3? Well, B is going to be randomly chosen between 1 and 2. Half the time it'll be 1, half the time it'll be 2. And like I said, Q, because of pi, or there's a bunch of ways of thinking of it. Essentially, all 3 of these are going to be randomly distributed, uniformly. There's an equal chance of seeing any possible thing satisfying this constraint. any triple like this.
Could you explain why B is just whoever 1 and 2?
That's just how we defined it in our conversation here. It's either the challenge, give me an isomorphism, or give me a map showing that G prime is equal to G1, or showing that G prime is equal to G2. Yes. So okay, so a conversation between a prover and a verifier in this case is just a triple, which is a graph, a bit, and a permutation. And it satisfies this, and otherwise it's randomly, uniformly distributed. And I say, a verifier can write one of these down. They start with B, they know what they're going to pick. Then they write down a random Q, just a random shuffling. And then they write down Q of GB as their G prime. So this will obviously satisfy this. And what it means for these three to be randomly distributed up to this equation, meaning that it still has to satisfy that, is you can kind of think of it as you started with 3 degrees of freedom, all randomly distributed, and you got rid of one, meaning once I pick 2 things randomly, the third one is determined. In the actual conversation, the things that were picked were G prime and then B, and then Q is determined after that. But you know, if I'm just writing down these conversations, it doesn't matter how I write them down in what order. I could determine B and Q, and then that, or sorry, I could pick B and Q, and then that determines G prime, and I could compute G prime easily from those two, going in a different order. So I could just write down a bunch of conversations between a prover and a verifier this way, and you wouldn't be able to distinguish them from a list of conversations that were actually had with a real prover and a real verifier. And thus, if you can solve any problem that you couldn't solve earlier using this, well, you actually could have solved it earlier. Just make your own conversations with a fake prover. So we've not given them anything useful, because they could have done anything with this information, G prime and Q, that they could do with this information. So this is actually kind of the formal definition of zero knowledge, is that the verifier can simulate the prover. The verifier can write down a transcript, and if they gave it to you, you wouldn't be able to tell if it was a transcript they made up or a transcript that they had with the real prover.
Earlier you got rid of the verifier, now you're getting rid of the prover. There's nothing left of the protocol.
Indeed. Okay, so this is why I didn't start with this definition of zero knowledge, because it makes no sense. Why would we care about such things? But really it kind of formalizes this notion that so long, if you're giving them random stuff, that shouldn't matter. You can even give them a little more than just random stuff. It's a way of checking that you actually have not learned anything new. Let me check what we're doing next based on time. I have 30 minutes.
35 actually.
Lovely. Well, I'm going to use those 5 minutes. Okay. Okay, so there's one other thing I wanted to point out about this. This shape of a proof, where the prover sends something over, the verifier responds with a challenge, and the prover responds to that challenge, has a special name. It's called a sigma protocol. It's called a sigma protocol because sigma looks like this. I was told, but what's it's backwards. I don't get, I mean, you'd have to ignore that. I don't get it, but I didn't make it up. So it's called a sigma protocol. That's a capital sigma in Greek. And sigma protocols are really useful, and they have some terminology associated with them. We call this a nonce. So you send over kind of a commitment to something random that you picked up, and later you're going to use that random thing, that nonce. Nonce means use only once or something like that, not but once, I don't know. And you're going to use that later to tweak the secret knowledge so that it looks random. That's kind of how you use a nonce. So you send over a nonce, you get back a random challenge, and then you respond to that challenge using the nonce so that everything is nice and hidden. And then every time you repeat, you have to pick a new nonce each time you do this. My Sudoku example also followed this. It started with me sending over encrypted values of every grid spot and my permutation. The verifier responding not with a bit, but with a 1 in 13 kind of thing. And then me responding with some keys that I came up with earlier. So you can think of the collection of all the keys as the nonce, or something like this. And then I reveal part of the nonce. All right. So I'm going to skip some of the things that I could have done, and if people want me to do them, I guess there's like an unconference happening sometime in a different room, and you can just ask me to do it. But it turns out that Sudoku, the example I gave you earlier, okay, wait. So I'm going to review a little bit of complexity theory that you might have learned if you have a CS degree like a long time ago and never used. And then I'm going to talk about some results and like when zero-knowledge proofs apply, when they exist. And then if we have time, we'll talk about Schnorr and digital signatures. So okay, to start, I'm just going to remind people, and if you have a question, just blurt it out. No need to raise hands. I'm going to be efficient as I can with the 30 minutes, but do ask questions. Okay, so you might have heard of these things called P and NP. To start, P is just things that you can do quickly in polynomial time, so to speak. So not exponential. You can very quickly do all the things we've seen verifiers do today. That all has to live in this set of problems that we call P. And then NP is the set of all things where there is a certificate or like a solution can be verified quickly. So as an example, finding out whether two graphs are the same might not necessarily be in P. I think that's an unsolved question. We don't know that it's in P, meaning we don't have a quick way of telling. But it's definitely at least an NP, because if I give you an F, you can check real quick that if I apply F to one of the graphs, I get the other one. So graph isomorphism lives here, but maybe not here. It turns out Sudoku lives in NP, and it actually is one of equivalent to the hardest problem in NP. Just a fun result. So these are called NP complete. So maybe I should have drawn it as like a picture, right? We have like P in here, we have NP here. We don't know if these are the same or not, but as cryptographers and Bitcoiners, we should all believe that they aren't. Otherwise, what are we doing with our lives? Oh man. And so under that assumption, we've got NP complete is a subset of NP, which is all of the problems that are the hardest in NP. And what that means is that any problem in NP can be efficiently reduced to that. You can rewrite it where this problem is only solvable, or this instance of this problem. So say I have like a graph isomorphism, two graphs. I can construct a Sudoku puzzle that can only be solved if the two graphs are actually the same. That would be a reduction. So it turns out that Sudoku lives here. Lots of other cool problems live there, which sucks. But not for us. We like them for today.
So you've got the P, the circle with P in it resides inside of the larger circle, which is NP?
Yeah, so NP means that you can check a solution quickly, and one way of checking a solution is just computing your own. And so if you could compute your own quickly, then you could certainly check it quickly. Verification is always easier than actually solving the problem, is another way of putting this. Or at least as hard. Or at least as easy, I don't know, one of the two. Okay, so these are interesting to know about. I also care for today about P space.
It's down the hall.
I was waiting for one of those. All right. P space means that you can solve the problem using polynomial space. Now, if you can solve it, if you can verify if there's a certificate, like if a solution can be checked efficiently, then that's always going to be in P space, because what I can do is I can just check every certificate that could possibly happen. I don't look at the list of certificates, but I generate a certificate, I check it, throw that away. Generate the next certificate, check it, throw it away. And that's not going to use more than polynomial space, because I just reuse that space. If that went over your head, that's totally fine. All you need to know is that if it's an NP, you can certainly solve in polynomial space. This is much bigger. You can run, or you can have an algorithm that takes forever to run, but never uses more than a little bit of memory. Hopefully, Lightning nodes live in P space. All right. Cool. And then there's IP, which is the set of problems which you have interactive proofs for. So forget zero knowledge, just a conversation like giving F, right? Like in our earlier example of the graphs being the same, an interactive proof is just, here's how you show one is the other. So certainly NP is inside of IP, because you can just like give them the proof and then they check it. But it turns out, so we know this, it might be equal, but you know, probably not. And it turns out these are equal. There's a proof. Things that can be proven are exactly the things which can be solved with polynomial amount of space. I'm not going to explain this proof. You can find it near the back of like a senior year CS complexity theory book or something. That's where I found it. Okay, and now we can talk about some big results. So here's kind of the payoff. There's a theorem from 1990. Theorem means mathematicians were involved. And the theorem is called all things provable are provable in zero knowledge. That is to say, IP equals ZKP. And this is big and, in my opinion, unintuitive. Anything that I can prove to you by giving you all my secrets, there is a way to prove to you while giving you nothing, no information about any of my secrets. And in particular, you know, this includes all of NP, which is normally what we care about for cryptography. We want validation to be efficient. So if I can give you all of my secrets and you can check it quickly, then you're an NP. And we saw problems in NP complete that have sigma protocols. So everything in NP has like one of these shaped protocols for zero knowledge, which has a nonce, a random challenge, and a response that uses the nonce. So everything in NP, which is basically like all the things we deal with in our day-to-day lives in Bitcoin and cryptography, not everything in cryptography, but most things, have a sigma protocol and have zero knowledge proofs. And furthermore, this challenge is always random. Right? It's like a 0 or a 1 or a bunch of zeros and ones or something like this. And I have lots of time, so let's talk about Schnorr now that we've kind of reached here. So, you know, let's take a step back. Public keys and private keys. We like to pretend that public keys are like some kind of identity. And I claim that you need to actually know some stuff about zero-knowledge proofs in order to make this claim validly. Sure, it's easy to encrypt things to public keys, that only people who have the private keys can read those things. This is oftentimes kind of introduced to people who do cryptography because it's quite easy. But really, at the heart of the matter is, if you don't have some way of proving that you know the private key, then it's not really an identity. An identity protocol should be a zero-knowledge proof that I know a private key to a given public key.
Signatures.
Yeah, so that's where we're going. So there's two stops on the way there. So we have, if you have a hard problem, then in some sense, you have private keys and public keys. You've got the solutions to those problems and the problem statement. So like earlier, we had G1, G2, that's the public key, and then the F that sends this to that, that was the private key. So you generate a random private key, you've got a graph, you can generate this public key. And okay, but how do I prove to you that I know F? Well, we did that, right? You follow that protocol from earlier where you send them a random permuted third graph, they ask you to show you that it's one of these two, they send over like a 1 or a 2, and then you respond with a permutation that looks random. And that was a zero-knowledge proof. Okay, so that's kind of like, I'm now convinced that having G1 and G2 as a public key kind of can be an identity, and it's the identity of the person who knows the shuffling of one of them that gives you the other. The person who knows F is kind of a way to think about that. But okay, so let's change this up to things we actually care about as Bitcoiners. Where did I throw the eraser?
So people that say that Bitcoin doesn't have zero-knowledge proofs, they're wrong because it can verify signatures.
Definitely. Digital signatures are a non-interactive zero-knowledge proof, which we're about to get to. So okay, we've got a prover. Here, I'll redraw this. So now, say that we have a public key. I'll call it capital X. Yeah? And the prover knows some little x. That's the private key. And the prover wants to prove to the verifier that they are the person who knows little x for this big X. For those of you who are comfortable, this is little x times capital G. For those who are not comfortable, stick around. Asher will tell you in about 20 minutes what this means, I think. Okay. All right. So we have this public key, which is known to both parties, this private key, known only to the prover. We're going to do a standard sigma protocol, which we know should exist because if I just tell you what the private key is, doing this multiplication is efficient. And so that means that this is an NP. There's efficient verification of a solution. And that means that NP is a smaller thing than ZKP. And ZKP has a zero-knowledge proof. And furthermore, all of NP has these nice sigma protocols. OK, so we're going to send over a nonce. So we generate a random number, as usual. And we send over R, which is kind of the public version of that number. So if we generate like a new private key, and we send over a public key corresponding to that private key.
An ephemeral key pair.
Yeah, one-time use. Nonce. And then the verifier responds with a random challenge. In this case, it's a number in our number field. Again, ask Asher later. It's just a number, E, chosen randomly. And then the prover responds with S. And they pick S to be, well, they want to make sure to use the private key. And they want to respond to the challenge. So they multiply their private key by the challenge. But if you send this, then you can like divide. So that's not good. So we add our nonce. So we used our nonce to, like, we added a random number to it. And so now that's not going to reveal information, I claim, and it won't prove. Read my blog post. And then the verifier checks that S times G is equal to R plus E times capital X. Just want to explain this really quick. Essentially what we do is we multiply both sides here. We take these numbers and we turn them into public keys. So this, the public key for little s, is S times G. Getting a public key just means multiplying by this big G. And then multiplying each of these things by the big G, K times big G is just that R from earlier, that nonce. And then the big G gets multiplied into this X to get this capital X. And so that's why this is the verification equation. And this is an identity protocol. This should convince the verifier that the prover knows this little x. Why? Well, I'd have to argue that it's complete, it's sound, and it's zero knowledge. And I do that in my blog posts.
So the claim that you're making is that the protocol is these three steps. The first step is that the prover sends R equals K plus G. So what in that first step, the prover is sending R?
Yes, they're sending R. And I'm just telling you, like in parentheses, what R is they have this random number and they generate the corresponding public key for that random.
The next step is that the verifier takes R and develops or generates E?
Yeah, so E is just some random number.
So the verifier just gives them E.
Yeah.
And
then the prover constructs a number that required use of their challenge and of the private key. There's a proof, that's in my blog post, that this S cannot be constructed without the use of this X and this E. And it utilizes the fact that if you reused nonces, then you'd be able to derive private keys. Awesome.
This is just Diffie-Hellman or whatever? Is that
No, so this is the Schnorr identity protocol. Yes, Diffie-Hellman is for encryption. Good question. Yeah, so encryption is one of the important things in public-private key, kind of when we say public keys are identities, but this is really the crux of it, is you can prove, without giving anything away about your private key, that you know the private key to this public key. Okay, and now I've been talking about it for forever. Let's get rid of the verifiers and make this a digital signature. Okay, so in a Sigma protocol, and some other kinds of protocols where the verifier only generates random values, right? They're only responding with random things. We should be able to replace them with a hash function. So here's how I'm going to do that. It's kind of like a silly way. I'm going to just say like E equals, and then you take the hash of everything that is known so far. So that's the public key and R. Yeah, so we've got capital X and R. So we take all the public things, everything that you take the nonce, and you take whatever's in the initial setup, and you take the hash of that, and we say that that's E. And now we don't need a verifier. Like, what the prover is going to do is they're going to generate a random number that gives them a nonce. Then they can compute the challenge, which will just be the hash of their public key and that nonce. And then they're going to create the response to that challenge that they generated. And the key thing is that hash functions are awesome and hopefully act like random oracles. And if you assume that they act like random oracles, then you can spend a couple hours understanding what that means and see that this isn't gameable. Like, it seems like maybe it should be gameable, but it isn't gameable. You can't like pick an R in a fancy way that lets you game this. Hash functions actually like make things nice and random in a way that you can't game or predict. And so what this lets you do is you generate the nonce, you generate this E for yourself, and then you generate this S, and then you publish the R and the S. And then anyone can take this R and this S, and they can take that R, compute the challenge that came from that R, and validate your response. And there was no conversation necessary. I can publish this on a blockchain under a transaction input. And this is the Schnorr digital signature. That's all it is it's a nonce, i.e. an ephemeral public key, and a number that satisfies the equation that I want to write down.
ECDSA signatures also have an R and an S value.
They do. It's confusing. S equals R, or sorry, S times G equals R plus that E, which is times X. And that's the Schnorr verification equation. And it just comes from taking the Schnorr identity protocol, which is like the sigma protocol that should exist for all things in NP, and then you get rid of the verifier, and you replace it with a hash function. And that gives you, that turns an identity protocol, or any hard problem gives you an identity protocol. Any identity protocol gives you a digital signature algorithm in this way. And that's how you get Schnorr. And honest verifier zero knowledge, which honest verifier zero knowledge is good enough now because we replace our verifier with an honest hash function. Hash functions don't lie. So that is the Schnorr digital signature. And this is how you turn hard problems into identity and signatures. Oh, and I guess for the one thing for this to be signature is you also add like a message into this hash that you want to sign. But that's just, you can do that for free. You put the message into the context. Like the message is the thing that they want to prove that the person who knows the private key likes that message. And so since it's in the context, now you add it to the hash. That's it.
What if it's more than 32 bytes?
Then you take the hash of it. Or something. I don't know. Ask Andrew Polstra.
Hash functions take unlimited data and you just set it up and run it.
That is at least one way of doing it, is you can take the hash of it to make it a 32-byte message. Actually, no. You could also just put the message. It's going in the hash function. So. Yes?
Is there some variation of this where you publish something slightly different? I seem to recall there's a slightly different verification.
Yes. Instead of R and S, you can publish E and S. And that'll do the same trick.
How does that, what is that?
Yeah, so you just put this hash out there. And then if you know the hash, there's a way of like solving for R. Yeah. You just like reverse some equations. But this is why everyone prefers R and S, and Bitcoin uses this as the serialization for signatures.
Does R mean the same thing in ECDSA as it means in Schnorr?
It's a nonce. Yeah, it's going to be you generate an ephemeral private key, and yeah, you get a nonce. So basically.
In fact, ECDSA was a way to sidestep the Schnorr practice.
Yes.
So
it's essentially instead of like multiplying, you add X and E. But then you have to like multiply by the K, and that introduces some problems, and you sidestep them, and you get ECDSA. So if instead of generating a value S that required use of these two things, instead of multiplying, I added, then there's some tricky way in which you can get ECDSA out of that, and it turns out to be worse because it requires more tricks. Whereas here, you just multiply, tweak it, you're done. That's why Schnorr's better.
Thank you, patent law.
Okay.
Can you find your blog post?
Assuredbits.com/blog. Come to me after if you can't find it. But I'm over time, so.
You're not quite over time.
Oh, okay. I'm on time. Awesome.
On time. We'll make sure to get that information if you would like to look at the blog post or put it in the Telegram.
Yeah.
What was this, SuredBits?
Yeah, suredbits.com/blog. And then if you go to like the category cryptography, I wrote all of those. And there's like a Schnorr series that covers some of the details for soundness and completeness and honest verifier zero knowledge.
Thank you for making the